Hey guys, we are going to be starting off our stoichiometry unit today. Stoichiometry does use a lot of those conversions that we learned in moles, but it applies them to reactions themselves. So we'll actually be able to convert between different substances, whereas moles we were only dealing with one substance. So for stoichiometry, we are going to be using balanced chemical equations as a basis to calculate how much reactant is needed to make a certain amount of product, or to figure out how much product will be produced during a reaction. And stoichiometry is the calculation of quantities in a chemical reaction, and make sure that this is going to be using balanced chemical equations. So you always want to double check and make sure your reaction is balanced before proceeding with any calculations. We're still going to be able to interpret our chemical equation using any type of particles, whether it's atoms, molecules, or formula units, moles, mass, and volume. But do remember that the mass and number of atoms are conserved in a chemical reaction, so that's why the reaction must be balanced. What we're going to focus on today is your one new step you're going to be learning with stoichiometry, are mole ratios. So this is going to be a new conversion factor we have not used before, but it's a conversion factor derived from the coefficients in your balanced chemical equation interpreted in terms of moles. So this is what will allow us to convert between different substances. So we'll be able to convert from moles of reactants into moles of products, or one reactant into another, one product into another. So if we're finding mole ratios of an equation, you're using only the coefficients. So remember, coefficients are the numbers in front of the substance themselves. So we have one nitrogen, compared to 3 hydrogens compared to 2 ammonia. So because that's what's in the balanced reaction, that can be used for any conversion. So say that we had moles of nitrogen and we wanted to get into moles of ammonia. Moles of nitrogen would move to the bottom, moles of ammonia would move up top. Our mole ratio, we would plug in those coefficients. So there's 1 nitrogen per every 2 ammonia. So that is going to be our conversion factor that we're adding in to our mole problems that we've done before to make a stoichiometry reaction. So let's look at some examples of just adding in mole ratios. We're going to do some longer problems later, but just focus on the mole ratios today. So here's a problem. We have the same overall reaction of nitrogen, hydrogen producing ammonia. Wants to know how many moles of ammonia are produced when 0.60 moles of nitrogen reacts with hydrogen. So just like we do any other problem, you're always going to start with what's given. So we're given the 0.60 moles of nitrogen. And here's where I told you to get used to writing the substance. That way you can make sure that you are canceling out appropriate units. We're looking for moles of ammonia. So we no longer need moles of nitrogen. So that will go in the bottom of our next step. And we can change into moles of ammonia. Based off of our coefficients, there are 2 moles of ammonia in the reaction, 1 mole of nitrogen. That will cancel out our unit of moles of nitrogen, leaving us with moles of ammonia. So we're ready to calculate. Since both numbers are above the line, we're going to multiply them. So 0.6 times 2. And remember, in terms of sig figs, our original number had 2 digits, so our answer should have 2 digits. So it's going to be 1.2 moles of ammonia. And that is your only new step for stoichiometry that we have to learn. Let's look at a couple more examples before you go on to practice. Here we have a different equation. We have aluminum and oxygen producing aluminum oxide. Our equation given is balanced. And it wants to know how many moles of aluminum are needed to form 3.7 moles of aluminum oxide. So you're always going to start with what's given. So 3.7 moles of aluminum oxide. We are looking for moles of ammonia, or moles of aluminum, excuse me. So the moles of aluminum oxide will go on the bottom. Moles of aluminum go on top. According to our balanced equation, we have 4 aluminum and 2 aluminum oxide. That's going to cancel out moles of aluminum oxide. And then we can calculate. So we have 3.7 times 4 divided by 2. Our original number given had 2 sig figs, so our answer should have 2 sig figs. So that is going to be 7.4 moles of aluminum. Let's keep going. Here we have the same equation given, but now we want to know how many moles of oxygen are needed to react with 14.8 moles of aluminum. So you're not always going to have to go from reactants to products or products to reactants. You can use this to figure out how much of each reactant you need. So here, start with what's given. So we have 14.8 moles of aluminum. We're looking for moles of oxygen, so we no longer need moles of aluminum. So that will go in the bottom of our next step. Moles of oxygen will be on top. According to our balanced equation, we have 4 aluminum and 3 oxygen. That's going to cancel out moles of aluminum, leaving us with moles of oxygen. So anything above the line you multiply, if it's below the line you divide. So 14.8 times 3 divided by 4. And our original number had 3 sig figs, so our answer, we can have 3 sig figs. So that's going to be 11.1 moles of oxygen. Let's do one last problem. Here we have the same equation, but we want to know how many moles of aluminum oxide are formed when 0.78 moles of oxygen reacts with aluminum. Go through the same process. Start with what's given. So the 0.78 moles of oxygen. Since we're looking for moles of aluminum oxide, we no longer need moles of oxygen, so it will move to the bottom. We're looking for moles of aluminum oxide. And do pay attention to which substance you are changing into. A lot of people just look and see aluminum and they change into aluminum instead of aluminum oxide. So make sure that you are canceling out and changing into the appropriate units. According to our balanced equation, we have 2 moles of aluminum oxide for every 3 moles of oxygen. That cancels out our unit of moles of oxygen, leaving us with moles of aluminum oxide. So when we calculate, we're going to do the 0.78 times 2 divided by 3. And our answer, we can have to 2 sig figs. So that's going to be 0.52 moles of aluminum oxide. Make sure you're practicing these skills, and starting tomorrow we're going to do the longer stoichiometry problems where we add in all of our other steps we learned from the mole.